Good. Now we have it. Okay, so what else are we going to do? Let's take a look at the drawing here. You remember this drawing, right? A particle that's subjected to a magnetic field and has a vector velocity perpendicular to the magnetic field will undergo uniform circular motion. Okay, so that's what we have to write that down there. And a particle subjected, a charged particle subjected to a uniform B field, having a velocity vector perpendicular to the field, will undergo uniform circular motion with the magnetic force perpendicular to the vector velocity. Okay? Because the speed, right? Or the magnitude of the velocity vector does not change, okay? It means that the work done by the magnetic force will be zero, okay? And also not just because the velocity doesn't change, but also because the force itself is perpendicular to the velocity vector, okay? Magnetic force makes a 90-degree angle with the velocity vector. Consequently, the work done by the magnetic force will be zero, no matter what the circumstance. Is the work done by the magnetic force. Remember, any force that is perpendicular to the displacement, that's physics, that is physics 6, right? The displacement of a particle will do no work whatsoever. What else can we do is that? Let's go back here to this uniform circular motion of the charged particle. Okay. Another thing that we can do here is that given this charge here must be here. Okay, that's the velocity vector must be here. Here's the X and Y axis. Okay. Let me rotate this guy so it looks better. If the charge is negative, then the force is going to go the other way. Make sense? Right? If here's a positive charge, what about a negative charge? If you have a negative charge, then the force is going to be opposite to this one, and the particle will undergo a uniform circular motion in this direction here, in this circle, if the particle were to be negative. Okay. Now, what else can we do with this type of motion? We can calculate the radius of curvature of the circle, right? Given the magnetic, given B, Q, and V, find the radius of curvature of this type of motion. Okay, so that's what now example, right? Let's do it. Treat that as an example. Example 1. Given a particle of charge Q. Okay, given a particle of charge Q subject and velocity V, right? And velocity V subjected to a uniform magnetic field. the velocity vector is perpendicular to B. Find the radius of curvature of the trajectory of this particle. Okay. So that's a nice problem of uniform circular motion that you saw back in physics 6. Solution. Let's get an equation here. Okay, we're going to let's use this one instead. Because the angle between the velocity vector and the magnetic field is 90 degrees. So we can write down that the magnetic force applied to this charge is going to be QVB. Okay, here's the magnetic force. Here's the magnetic force. Okay, you got magnetic force makes an angle of 90 degrees with the velocity vector. Consequently, the magnetic force does no work whatsoever in this particle. By what we mean by doing no work whatsoever in this particle, it means that the speed of the particle doesn't change. Okay, that's what it means. It means that the speed of the particle doesn't change. The velocity vector may change, and in reality, in this case, the velocity vector is changing direction. Okay, but the speed doesn't change. It's uniform circular motion. And that's contrary to the electric field, right? The electric field alone can accelerate a charged particle. That's an important difference between those two forces. Okay, so here you go. QVB. Q is given, V is given, B is given. Now we want to find the radius curvature of the trajectory of this particle. Okay. Since we know given particle trajectory subject to a uniform only, right? I'm gonna put it here only. No other forces applied. I'm gonna put here the particle is subjected only to the magnetic force. Nothing else. There is no other force. There is no electric force there. There is no gravitational force, right? So we can use this. So we can state, based on that, we can state that the magnetic force is equal to the net force applied to the particle. If the net force, and according to Newton's second law of motion, right? Net force is equal to mass times acceleration. And that's the nice thing about Newton's law of motion. When it was formulated, people only knew about mechanical configurations, right? They didn't know anything about those invisible charged particles. And despite of that, Newton's law of motion still hold at the microscopic level. Okay, and then now that we have MA, and we also know that the particle is undergoing uniform circular motion, we can recognize that this acceleration is going to be the centripetal acceleration. If it's the centripetal acceleration can also be written in terms of the velocity square divided by the radius of curvature. Okay, that's how you solve this problem. That's how you solve that, and that's what we know. And by the way, given a particle of charge Q, here you go. I gotta put the mass of the particle to mass M and velocity V, mass M and velocity V, subjected to a uniform magnetic field. So you need the mass as well to solve this problem. Okay, whether it's an electron, a proton, subject to a non-uniform magnetic field, find the radius of curvature of the trajectory of this particle. The particle subjected only to the magnetic force. Okay, and now we can copy this one here, paste here, and solve. Let's see, can you do any simplifications here? Yes, the velocity here is going, the velocity on the left side is going to cancel out with the velocity on the right side. Okay. And we can solve for R. Oops. MV. Like that. And then we solve for R. QB, right? R is equal to QB. QB. R MV over QB. Okay. Then you can start applying some, numerical values to this, to this equation, right? Like electron mass, electron charge, given, and given a velocity for the electric charge for the electron, and the magnetic field value of and the value of the magnetic field, right? Then with this equation, you can then apply it to different circumstances to get some numerical values. For instance, an electron of velocity, of a given velocity subjected to the magnetic field of the Earth. Okay? To the magnetic field of the Earth. That's can also give, right? Well, for example, and then you can also, let's see, doesn't have to be an electron, can be any other charged particle, a proton at a given velocity, right? At a given velocity, subject to magnetic field of the Earth. Can be an ion at a given velocity, subjected to the magnetic field of a device, okay, and so on. Okay, what else can we do is that we can also do, another example here, example 2. Find the period of rotation of this electric charge. Okay, so here we go. We have the situation that the particle is moving with a constant speed, not constant velocity, but constant speed. And it's going to take a given amount of time, a period, to complete this full circle. What's going to be this period, right? Find the period of rotation of this electric charge, okay? Solution. Another one. We do know that the period of rotation, T, is going to be, don't forget the full circle, let's say, the full circumference, right? The full circumference of the path of this charge is 2 pi r. I'm gonna put that big C equal to 2 pi r. Oh, I meant 2 here. 2 pi r, which is 2 pi mv over qb. Okay. That's we also know that, you know, find the period T, right? Rotation of this electric charge. Of translation, shouldn't be rotation, should be translation, right? Translation of this charge. Rotation, you know, rotation implies that the particle is rotating around its own axis, okay? So, which is not the case. The particle is rotating about the center of the circle. What's the period of this translation, this translational path, right? So here you go. We also know that V times T, which by the way, we do not know what T, we want to find out T, is also equal to 2 pi r, right? Is equal to the circumference. And now we can solve our problem. That's the key to solve our problem, recognizing that Vt is equal to 2 pi r. And then we can start simplifying our equation. V cancels with V. And look what we get. 2 pi m over qb. Okay. Note that the period of translation depends only on the mass, depends on the magnetic field, on the magnetic field intensity, the mass, and charge of the particle. It does not depend on its, it does not depend on its speed, v, right? So if you want to change the period of rotation, the period of translation of this particle, the only thing you can do of a given part, the only thing you can do is by changing the magnetic field. Okay, so for a given charge, a given charged particle, comma, the only parameter that affects its period is the magnetic field intensity. Magnetic field intensity. Okay. The stronger the magnetic field, the stronger the force, the stronger the magnetic force, and the faster the particle moves, the shorter the period, right? Here you go. The stronger the magnetic field, the stronger the magnetic force is, and the shorter the period of translation of the particle. Okay? And the short, or the higher, right? It's the particle's frequency. Higher the particle's frequency. There is a relationship between the period, right, and the frequency. And you know, you can write that formula as 1 divided by f. It's like that. You know, if you want to increase the frequency of a charged particle in a magnetic field, all you have to do is to increase the intensity of the magnetic field. That's what we have for this part. And now we are ready to start something else. very important. And those are devices that hopefully you're going to be exposed to in your professional life. Okay, one of those devices is here, the velocity selector. Okay, we have the velocity selector, you have the mass spectrometer, and you have some other devices out there that use the magnetic field. Okay, here you go. Here is the configuration of the velocity selector. I'm going to get into the details of this device, but in addition to the velocity selector, you also have the mass spectrometer. The mass spectrometer is a combination of the velocity selector with an outside magnetic field. We're going to get into the details of this device, and I can even animate it a little bit more, right? Here you go. The next one, the particle would be in a different position here in the circle. Let's see. I'm going to get this one here. No, I don't want to do that. And I want to rotate it. Let's see. You got it? Oh, nope. I gotta see, gotta group that first. Yeah, now that we group, we can rotate the whole thing, you know, and put it somewhere around here. That's the, and I'm doing that for a positive charge. If you're a negative charge, it would be different, right? How do I get the magnetic force? The magnetic force is obtained from the velocity vector cross, hey, wait a minute. Velocity vector cross magnetic field. Magnetic field is into the board. So velocity vector cross magnetic field is to the left, right? Initially to the left, but because now the particle has this inertia, it will tend to move in a circle. Okay, I can continue with the, oh, here you go. I can continue with this simulation. One more student coming. Okay, can continue the simulation. And I'm going to rotate a little bit more. You know, it's important that you practice those illustrations, but it helps if you practice on your own. It helps a lot if you do the drawings yourself. It helps a lot to understand, not just understand, but memorize to how this device works. This mass spectrometer. Here we're just talking about the qualitative configuration of this device, getting to the detailed calculations. Okay, now we have our movie, right? See, we have this particle moving towards this. You know, what we have a velocity selector here. Well, the first thing that you have to know about the velocity selector. The first thing that you have to know about the velocity selector is that it is a combination of electric and magnetic fields. What you see right in here is the parallel plate, right? Positively charged and negatively charged. Okay, why do you have this parallel plate? So you can create a uniform electric field in this volume. Okay, and I'm gonna go the details right in here. Here you go. I started this one. Velocity selector. Negative plate, positive plate, electric field from the right to the left. If we place, and then we combine, if we combine an electric field with a magnetic field, something interesting happens, okay? For the motion of a charged particle. Of course, they must have some specific values for the electric field, right? So what happened? I put an electric charge right here in this volume. We see this electric field, uniform electric field. The particle is positive in this case. this particle will be subjected to an electric field to the left, right? Those negative charges are going to attract this positive charge. But also, because this particle is subject to a magnetic field, V cross B is going to result in a magnetic field to the right. Okay? If we tune the electric field with the magnetic field in such a way, we can come up with a magnetic force that is equal to the electric force. It's possible to do that in real life. Okay? You can change the electric potential between those two plates, or you can adjust the magnetic field just by increasing or decreasing the current of your circuit that's creating the magnetic field. It's possible to do that. Okay? And then if you do that, this particle, the net force in the particle is going to be zero in this charged particle. Even though the force, the electric force only applied to the particle is not going to be zero, even though the magnetic force applied to the particle is not going to be zero. But if you choose a proper electric field intensity and a proper magnetic field intensity, you may get a net force equal to zero. I'm going to show you how to do that. Okay? If the net force is equal to zero, the particle is going to move with constant velocity along this volume, right? There will be no work done by the net force. By the net force, right? Net force is equal to zero. Consequently, the net force is not going to do any work whatsoever in the particle. Okay? So now you know how the velocity selector works. The velocity selector. Let's talk about the velocity selector. Velocity selector. Here you go. The velocity selector is a device that selects or filters charged particles of a specific charged particles that have a specific velocity vector. Okay. Okay. In this device, the net force applied to the charge is zero. Okay. In this device, we use electric and magnetic fields. Electric and magnetic fields. To ensure that the net force applied to the charge is zero. So we can filter out particles of a specific velocity, okay? And what's going to be this specific velocity, okay? All you have to do is to look at this configuration here that you saw. The electric force must be equal to the magnetic force, okay? If the magnetic force is greater than the electric force, then this particle is going to deviate to the right, right? And it's not going to go through this volume, through this empty space. On the other hand, if the electric force is greater than the magnetic force, then the particle is going to be deviated to the left side, right? The velocity selector is to ensure that particles of a given velocity goes through it. Okay, so let's see what this velocity is. Okay, the velocity selector. Velocity selector is a device that selects or filters charged particles that have a specific velocity vector. This device will use electric and magnetic fields to ensure that the net force applied to the charge is zero. So you can filter out particles with the following speed, right? With the following velocity. Let's put this here with the following velocity. Okay. The condition for the velocity selector is the following. Magnetic force must be equal to the electric force. Okay. Magnetic force is going to be QVB. Electric force is going to be QE. Okay, and look here at this mass, what's happening here. The Q cancels with the Q here, see that? And then we can get a velocity that's going to be equal to what? E over B. If your velocity is equal to this ratio, if the velocity of the charged particle is equal to this ratio, then the particle will move in a straight line. We see the volume of the velocity selector. Okay, so that's what happens if you have this condition satisfied. The particle moves just like that, right? Otherwise, no. Otherwise, if the particle is moving with V greater than E divided by B, right? What does it mean? V greater. V greater of E divided by V. Let's take a look here. What's going to happen? You know, the magnet. Oh, did I put it here? The magnetic force. Okay, the magnetic force is going to be given by what? It's going to be given by QVB, right? And now let's see, greater than is going to be given by, your magnetic force is going to be given by E over B. E over B, right? And then we end up with QE. Let's see if I can do it in the right way. I gotta do it in the right way here so you can understand it. Here you go. We'll put like that. F of B, magnetic force divided by QB. Okay, QB. And now I'm saying that this QB is going to be greater than E divided by B, right? E divided by B. That's what I'm saying. Consequently, this is an inequation, right? Consequently, my magnetic force is going to be what? Greater than QB. Right? Greater than QB. Which, by the way, is greater than the electric force, right? Here you go. What if, here you go, I'm gonna put it this way. What if the particle is moving with V greater than E over B. You know, magnetic force is going to be QVB. And then we are making a statement here that V is greater than E over B. This ratio is going to be greater than E over B, which implies that the magnetic force is going to be greater than, I'm going to put another step here. So we can go. Yeah, I'm going to put like that. QB times EB, E over B, okay? This B cancel out with B, and we end up great with QE right here, which implies the magnetic force is going to be greater than the electric force. Under this circumstance, right? Under this circumstance, what's going to happen to this particle here? The magnetic force is going to be greater, and the particle is going to deviate to the right. Okay? I'm not going to make a drawing here, otherwise it's going to take too long. What if, what about the opposite? What if the particle is moving with V less than E over B, right? Here you go. All you have to do is to switch the signs here. The magnetic force is going to be less than the electric force, and the particle will deviate to the left. Okay, in the volume there, in the drawing that I put to you. In this case, okay, the particle will, it's very difficult to study the type of motion that this particle will undergo, but at least we know that will deviate, will initially, right? Let's put it, will initially deviate to the right on the illustration. Okay, initially, because there is still a, you know, a combination of circular motion in there that's very difficult to describe at this level in the course. Okay, in this case, in the illustration, we go. In this case, the particle will initially deviate to the left in the illustration. Okay, so will collide is the same, right? And it's not going to go through the volume. Will collide with this other one. So that's the velocity selector. Okay. Okay, so how do you see if the particle went through or not? Okay, the way you do that, let's see if I have it. Here's a little bit. I put the electric field to in the other direction. Okay, how do you know if the particle really reached the other end? There's a way to know that. Okay, there's a way to know that. You can get a screen, a phosphorescent screen right here. A screen made of phosphorescent material. Say I want to do the same to be filled with white, and I'm going to send it to the back. In Prati, right? Yeah, okay. In Prati, what do? You come up with a screen made, can be a piece of paper. Oh, thank you. Thank you, Kennedy. Sometimes I hear those things and I don't let the student come right away, and I forget it. Sorry. I forget the student was waiting. Okay, so phosphorescent screen. Oh my, too big. Screen made of a phosphorescent material. Font. Yeah, what is the font here? Yeah, too large. Let's see, 14 maybe. Phosphorescent. Oops. Phosphorescent screen. Okay. And people use that to see particles colliding against a given target. So the moment the charged particle reaches this screen, you're going to see a little flash of light, just like this, similar to that that of the northern lights, phosphorescent screen like that. Okay. Let me see if there is anybody else there in the waiting room. Participants, nobody else. Okay, good. Okay, so that's one device. I don't need that anymore. If the electric field were in the other direction, right, the magnetic field would have to be in the opposite direction to get a uniform motion of the charged particle. Here, the magnetic field is coming out towards your face. Here, the magnetic field going into the plane of my screen. Okay, phosphorescent screen. Should be something like that covering this entire exit here. Otherwise, you might lose those particles that are moving closer to the right or left plate. Okay. Okay, here's another illustration of the magnetic force. Okay, V cross B is into the board, the particle is positive, right? V cross B. So consequently, it's going to be in the Z direction. Here's the axis. I put x-axis upwards, y-axis to the right, and the Z direction is into the board as well. Okay, another drawing here, and okay, now let's talk about the mass spectrometer. Okay. The velocity selector is very important in the mass spectrometer. Another important device is the mass spectrometer. The mass spectrometer uses the velocities, is made up, mass spectrometer is made up of a velocity selector plus an external magnetic field. So in order for you to understand the mass spectrometer, you have to understand the velocity selector. For you to understand the mass spectrometer, you must first understand the velocity selector. Okay. So how does it work? Okay. Again, the mass spectrometer is a velocity selector plus something else. Okay. A velocity selector, a slit as well. Usually this distance here is very small, okay? Don't be fooled by the drawing here. It's so small that we can come up with a slit that is like that, okay? And so this guy extends further down here, extends further down here. That's how, you know, we do that because we may have other particles passing to a place closer to the positive or the negative plate. Okay, so here we go. I'm going to replace what I have here in the other drawings. Here you go. So the mass spectrometer is made up of the velocity selector plus an outside magnetic field. The outside magnetic field doesn't have to be the same value as the magnetic field on the inside. Okay, they have both the same. They can also have opposite directions too. Okay, here I put them in the same direction, but because they're written a different way, it means that their intensity doesn't have to be the same. Okay, so how does the mass spectrometer works? First, you put together a velocity selector. A particle moves with constant velocity through this volume of the velocity selector. And when it gets out of the velocity selector, okay, now the only force subjected the only force that this particle is subjected to is the magnetic force, nothing else, because there is no uniform electric field there. That's how we build the mass spectrometer. I want to put the magnetic field a little bit further away here. Here you go. Note V cross B is to the left. The particle is positively charged, is not negatively charged. And then what happens when it gets into this outside volume? It will undergo uniform circular motion towards the left, okay? With this radius, with the circle is this given radius here. And what else? As the particle, this is a phosphorescent screen. As the particle moves in this circle, eventually it's gonna hit this phosphorescent screen around this region here. Okay. Okay, here you go. Oh, copy and paste, right? Copy and paste, and now you have more. Okay, so let's animate that. Here you go. The particle is going through the volume of the velocity selector. Eventually, it exits the velocity selector. The electric field becomes 0. And by the way, here is supposed to be B out, right? Yeah, it's B out. Force of the magnetic force of the outside magnetic field. Let's get that here. Click this one. We are almost at the point that we need to take a break. Yeah. I'm gonna get rid of this FB. Get rid of FB. Okay, I'll get rid of this one. Another one. Another one. Good. Velocity vector here. No, velocity vector here. Velocity vector here. Velocity vector here, right? And velocity vector here. And now I gotta put my FB out there. FB out. FB out. FB out. FB out. FB out. Okay. So here you go. So the story goes like that again. Just repeating the story over and over again, right? I'm going to write that down in the notes as well. The mass spectrometer. What does the mass spectrometer do? With this device, you can measure the charge to the mass ratio of the particle. Okay. So here you go. That's a very nice way of finding out the mass of an atom, or even the mass of ionized molecule, assuming that you know the electric charge. Here you go. the velocity, the particle is exiting the velocity selector. Once it exits the velocity selector, it's subjected only to the magnetic force. Being subjected only to the magnetic force makes the particle undergo a uniform circular motion. Okay. And, oh, I gotta do more here, right? Let's you'll do everything. Here we go. One more. Another. Yeah, here you go. And then I take this one out, 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 take this one out. Yeah, one more. This one out, this one out. Yeah, good. So we undergo uniform circular motion. And then we have, and don't forget, like I mentioned, you know, this width here is very small compared to the radius of curvature. This illustration is not in scale, okay? This distance here is very small compared to the radius of the particle. And here you go, the particle. And then eventually the particle collides against this phosphorescent screen. I'm going to put it right here, that's better. Okay. And when the particle collides with this phosphorescent screen, you see a little bit of a flash, again, similar to that of the Northern Lights. And then you do have a ruler here that can measure the distance of impact, and the scientists can measure the radius of curvature of the path of this particle. Okay, so let's write it down. Okay, another important device is the mass spectrometer. The mass spectrometer is made up of a velocity selector plus an external magnetic field. For you, okay? Okay, in the region of the velocity selector, only certain particles of a given velocity, E over B, exits the volume of the mass spectrometer. You know what's the velocity of those particles because you can adjust the electric and magnetic field. You adjust the electric field by turning in the electric potential. You adjust the magnetic field by adjusting the current in your device. Okay. Outside the velocity selector, we have a region of uniform magnetic field. Uniform magnetic field. Okay. In the region of velocity selector, only certain. And don't forget that we must have a uniform electric field here and uniform magnetic field perpendicular to one another, right? Outside, okay. Subjected to the magnetic force, with the particle being subjected to the magnetic, with the particle being subjected only to the magnetic force, the particle will describe a circular trajectory. Outside the velocity selector, we have two screens made of phosphorescent material. Right? Once the particle strikes the phosphorescent screen the screen produces a flash of light, similar to the northern lights that can be seen with the naked eye. The operator or scientist, right, then measure the distance of this flash of light to the center, to the exit, right? To the exit slit of the particle and find the charge to mass ratio of this particle. And how do we do that? We're going to derive that right now. Actually, we already derived that, okay? Actually, we already derived. So it goes according to that equation that you saw before, right? The radius of curvature of the particle is given by this formula. Okay, so let's so here you go. Let's not forget here is this B out. This R is measured. This B out is controlled, right? And this V, you already know that's equal to E divided by B, but it's a different B because it's the inner magnetic field, E over B. And this guy is measured, this guy is adjusted according to your experimental conditions. This one is adjusted, and this one is also adjusted. It's all those three parameters under your control. 1, 2, 3. Okay. And we can move this to the other side. Okay, we end up ME over B. Like that. By the way, I want to keep the Q on the other side because we do not know what's the charge. And then we pass the remaining of the equation to the left side. I'll call that B in. We can call that B in if you want. Okay. You measure that, you adjust all those three parameters, and as a result, you can obtain the mass to charge ratio of the particle. If you know the charge, you can find out what's the mass of the particle. Okay, and you can assume that the charge of the particle is -1 E, right? Because in general, it's much easier for you to produce an atom or even a molecule with one electron stripped out of it. So if you know what's the charge of the particle, you can determine the mass of the particle. That's the beauty of this device. With this simple experiment, you can determine the mass to charge ratio of the particle, of the charged particle. If you have an electron, you find out what's going to be the mass of the electron because you already know what's the charge of the electron. Okay. So that what we have is 9:57 right now. Well, another student coming in. And we have a lecture here. Let's take a quick look at the book, right? So we know where we are right now. Okay, the physics of the velocity selector, okay? Okay, capacitor plates producing a uniform electric field. Okay, they're done a charged particle through the electromagnetic field. Okay, here you go. Problem solved. The magnetic force always remains perpendicular to the velocity vector is directed toward the center of the circular path. Because the magnetic force is perpendicular to the velocity vector, the work done by the magnetic force is going to be 0. Okay, here's the ratio, right? Let's see if I got it right. MVQB. Oops, not this one. MVQB. Yeah, MVQB. Oh, not this one. This one here. MVQB. Motion of the proton. They have this, this example here in the book. Now they're coming up with actual numbers, right? That's radius of curvature of this proton that's been moving with this speed is on the order of 6 centimeters. It's not that small. It's very large. Okay, 6.6 centimeters. That's something that you can measure with a ruler. Can measure with a ruler, and that's because of the speed of the proton. Okay. Particle in a bubble chamber, we have those devices out there as well that we can visualize the path of a particle. And the mass spectrometer. Here you go. We did the mass spectrometer. An ion source that accepts. This one is a very simple mass spectrometer, okay? This is a very simple mass spectrometer that doesn't have any electric field in between. But you can build a mass spectrometer in this way as well. In this case, we have an ion source. This ion source is subjected to an electric field that accelerates the source from 0 to a given velocity. Okay, and once it exits this region, the particle undergoes uniform circular motion, right? And we have this detector here, just like I mentioned, is a phosphorescent screen that you can see the flash of light and measure the distance, the radius of curvature of the particle. That's another way. And you go solving. That's the mass. That's a different, like I said, that's a different experimental configuration. Okay, and 1001. Let's take a. We did 21.4 as well, and let's take a look at the. Attendance here. Randy, are you there, Randy?
Yeah, I'm here.
Okay, thank you, Randy. Vanessa Bonilla. Vanessa, thank you, Vanessa. Ashley Diaz.
I'm here.
Thank you, Ashley. Natalie Espinosa. Are you there, Natalie? I see Natalie here. I don't hear anything from her. I'm going to put it here. And next is Janet Garcia. You there, Janet? I see Janet in my list here, but I can't hear from her. Noor Hassan. Are you there, Noor? I can see Noor in my list, but I can't hear from her. Blanca Hernandez.
Here.
Blanca Hernandez, no? Kaylee Hernandez. Thank you, Kaylee. Joshua Jimenez. I don't see Joshua here. Okay, next is Alondra. Are you there, Alondra?
Yes, I'm here, present.
Okay, thank you, Kennedy.
I'm here.
Thank you, Daisy. Thank you, Daisy. Yesenia. Thank you, Yesenia. Next is Brian Ong. Okay, another one is, next one is Artur Pacheco. Artur Pacheco, I don't see Artur Pacheco here. Okay, Janet Garcia, right? Okay, thank you, Janet. I don't see Artur here. Labelut, are you there? Next is Donia.
Here.
Thank you, Elika.
Here.
Next is Brianna Valencia.
Here.
And Justena Youssef. Justena Youssef. Okay, thank you. And see how many we have. We have 16. 2 students. I didn't hear from 2. Natalie, are you there? Natalie Anul? Okay, I can't hear from you. And let's take our break. It's 10:05 right now. Break from 10:05 to 10:20 a.m. I see you in 15 minutes. Okay, I'm back here. Let's take a look. Yeah, let me do another drawing according to the book. Okay, so you have 2 different models of the mass spectrometer. Okay, I'm going to write it down. The mass spectrometer, you know, the mass spectrometer has a second configuration illustrated in the book. And in this configuration, the velocity selector is replaced by a potential difference, an electric potential difference that accelerates the charge from rest to a given velocity that can be calculated outside. The mass spectrometer has a second configuration such as the book. In this configuration, we have the following. One, the velocity selector is replaced with a device that applies an electric potential difference to the charge. The following, we go. The charge is initially at rest. It is then accelerated by an electric potential difference. It's like a battery, okay? Difference. Okay. In this case, the mass spectrometer has a second conclusion in the book. I'm going to put it here. In this configuration, because the velocity selector is replaced by an electric potential difference. Accordingly, we have the following velocity selector. Okay, here you go. The charge is initially at rest. is then accelerated by the electric potential difference, right? The rest, it's been accelerated by electric potential difference outside this region of electric field. We have is accelerated by electric potential difference through a slit, okay? Through a slit. Outside this region of electric field, we have a uniform, outside this region of uniform electric field, outside this region of uniform electric field, okay? Uniform electric field, we have a uniform magnetic field. The B field bends the trajectory of the particle towards a detector, okay, which can be a phosphorescent screen. Once the charged particle collides with the phosphorescent screen, it emits a flash of light. Again, similar to the northern lights, right? Similar to the northern lights. I'm going to keep on making reference to the northern lights every now and then here. Similar to the northern lights. The operator measures the position of this flash of light, measure the position of this flash of light. And from this measurement, he can determine the radius of curvature of the particle, okay? Like that. So if I were to illustrate that, I'm gonna use, almost everything here that I had, with the only difference now, see, the only difference now is gonna be like that. I start with this. I don't need to go. Okay, so instead of a combination of electric and magnetic fields, okay, you have just one electric field in this case. Okay, keep going. But there is more. Particle is initially at rest right here. It's produced, there are ways of producing charged particles. Okay. Particle is initially at rest. And what else? Group. Yeah, I don't need that. Oh. No. Group. Don't need that. Good. Have a source of charged particles. Hey, what's happening here? I'm getting lost already. See, nothing wrong. Okay. Yeah, what about that? Okay. right in here. Let me put that aside. Yes. Okay, here you go. Let's group that. This one has an important difference, okay? It has a hole here in this plate. Like that. Like that, okay? And then in this region, it has a really small hole in there, but the field is still uniform despite the presence of the hole. The hole is so small that it doesn't affect much the distribution of the electric field, okay? That's the configuration that your book has. Every book that I see out there, they do it the way that I did. One more. But this configuration also would work. Okay. So we end up having an electric force. Uniform electric field, constant electric force. Okay. And outside this volume, that's the first slide. There you go. Notice that in this case, is oriented differently. And what else? Okay, now I'm gonna need this one as well. Oh, so here goes here. In the next, okay. In the meantime, just repeat what I'm doing, right? Because it's gonna help you to memorize and understand how this whole thing works. Go. Accelerate the charge. Let's make the gap a little bit smaller, a little bit larger. Here you go. Like that. I'm gonna use the red arrow instead of the blue one. Oh, here you go. like I said, the charge is initially at rest. I can't put that V naught equal to 0, right? V naught equal to 0. And again, there are some easy ways of doing that. I'm not going to go into the details. Okay, further down here. Electric force. And now I gotta illustrate the velocity as well. Here you go. Yeah, here you go. Velocity of the charge. Just outside this region of electric field, the force is going to be 0, right? Now you don't have any force here. Electric force is 0. And I can put the velocity vector here. I think I'm going to move a little bit down. Yeah, better, right? Here you go. I have to adjust this one as well. The velocity. Good, like that. Okay, and now in this outside region, we have this outside magnetic field. Good, there you go. Rest, start accelerating. Because it's accelerating, we can increase a little bit the arrow length. Okay, and then what else? What comes next? Well, if you remember, right, what we did there before. And I'm gonna, and let's not forget our screen, phosphorescent screen that we had before. Phosphorescent screen. Send to the back. Send to the back. Back. Okay. Send to back. Okay, phosphorescent string, both sides. I want to do one with a phosphorescent string, the other without a phosphorescent string, otherwise it becomes too much, right? Like that. Go. And now the particle is ready to undergo uniform circular motion. I don't need that anymore. Just repeating what I had before. Yeah. I don't need that anymore. I don't need that anymore. I don't need that anymore. Okay, that's the one I want. Right? Right here. I'm gonna move this guy a little bit. Oops. Upwards. Like that. Yeah, this drawing is becoming very okay. Here you go. Be out. Don't want this. Let me take out those magnetic field lines here. Here you go. Positive charge. I'm gonna take it out a little bit more. Yeah, this one. And then the particle undergo the circular motion. Once it's collided with phosphorescent string, you're gonna see a flash. And the distance from here to here is twice the radius of the particle. Right? That's the other configuration that's described in your book. The other configuration of the mass spectrometer. Let's see. I think I raised the wrong one. No, I didn't. Okay. Okay, this one. I don't think I need this one. Oh. Okay. So and I'm gonna label that. Here's the velocity selector. Mass spectrometer 1. Mass spectrometer configuration 1. And then we have the mass spectrometer configuration 2 from the book. Mass spectrometer configuration 2 from the book. Okay. How do we determine this velocity? We determine this velocity just by, applying the acceleration due to the electric force. Okay, we did that before. And okay, here you go. Let's take a look. That's the mass spectrometer. Okay, and then we have the force on a current in a magnetic field. See if they have we usually teaches also the let's see. Magnetic fields produced by current. Okay. Yeah, they don't have the case of the synchrotron here. Let's see, yeah, they don't have. So let's continue here. (10:45). Don't forget our quiz is at 11:35, 1 hour from now, and then forward. Okay. Magnetic force applied to a current carrying wire. Okay. Okay. Note that a moving charge subjected to a magnetic field, moving charge in a magnetic field, is subjected to a magnetic force, right? Magnetic force. Since a conductor that carries a current, an electric current, also, since conductors has a moving charge inside it, right? Then it must also be subjected to magnetic force, right? Can you picture that, right? Let's see if I can illustrate that for you here. Skip that, maybe it's this one. Oh yeah, current carrying wire. Okay, so here you go. Here's my section of wire of conducting material carrying a current. Now, magnetic force. Magnetic force in a current carrying wire. Magnetic force in a current carrying wire. Okay. So here you go. This this wire can extend further to the left and the right. Okay. So think about that. We have a current carrying wire here. Current carrying wire means that electric charges are moving inside it, right? In this specific case, we can illustrate my charge that makes up my current carrying wire as positive charges that are moving in the same direction of the current. And again, like that. If we apply a magnetic field in this direction, right? And well, add one more slide, just like I have been doing with the so consider the story goes like that, right? Consider first a current carrying wire Oops. Consider first the current carrying wire. This current carrying wire can be pictured as current carrying wire of length L. This current carrying wire can be pictured at the microscopic level as several charges, positive charges moving inside it in the direction of the current. And go ahead and subject this current carrying wire to a uniform magnetic field that, by the way, perpendicular to this plane. Okay? Once you do the V cross B, you know, every positive charge that's here that's moving inside this wire is going to feel a downward force, right? Now I, eliminate the charge to simplify the drawing. I don't need this guy here. I don't need, okay, that's the L. So if you expose a current carrying wire to a magnetic field, you're going to see that this current carrying wire is going to be bent. It's going to be bent towards this direction. Current carrying wire, electric charges, visualize your electric charge there inside, apply a magnetic field, V cross B, the force has to be downwards. Okay? And the wire will tend to bend. If we put the XY axis there at the top, the direction of the magnetic force is going to be in the negative Y direction. So what's going to be the equation for that? What's going to be the value of this force? That's the question that we ask, okay? And that's a type of experiment that we can perform, that I demonstrate that we can perform that at the college. Unfortunately, I don't have the device here, but it's something exactly like that, okay? It's a magnet that produces a magnetic field. We put a wire inside this region here. It must have a closed current, right? A closed circuit wire. And if you flow the current in one direction, the wire moves in this counterclockwise direction. If we invert the current direction, the wire is going to bend to the left, okay? That's exactly what happens. And that can be seen easily. How do you do that? Let's take a look. Here you go. We have the equations here, right? And I'm going to derive step by step. Just go back to your QVB, the magnetic force, QVB, but don't forget now that we must have that sine of theta to get a more generic equation for sine of theta. Oops. Sine of theta like that. But now that we have a current carrying wire, we're going to have some electric charges flowing through it. So we here write our equation. In the following way. I am dividing it by delta T. I didn't eliminate my charge, I just changed the notation. And then to make this equation equal to the other one, what we have to do? We have to multiply by delta T as well, right? This equation is exactly the same as this other one. It's just in a different format. And delta Q over delta T is the current. And V times delta T is the length, the length of that section of the wire. Okay, so that's the magnetic force in a current carrying wire, in a current carrying conductor. Okay. And here you go, ILB sine of theta. And again, the direction of the force is given by the right hand rule. Okay. There are some practical applications as well. Okay. Here's a practical application of a speaker. Okay. So here you go. We have the speaker is inserted here in this magnet. We have this wire wound around the speaker. And we have this receiver that's varying the current direction back and forth. Okay, and as we do that, we change the direction of the force. Okay, and sometimes the force is to the right, sometimes the force is to the left, right? So look here, what's happened. Here's the magnet, right? North polarity here, south polarity here. This magnet is exactly the same one. This permanent magnet is exactly the same one. Here's my speaker. I get a cone together with a cylinder. I want a current carrying wire around the cylinder connected to a generator, can be a receiver, which can change the direction of the current back and forth with a given frequency. It's possible to do that too. Okay. When the current is flowing in one direction, okay, here out of the board and into the board, the force is going to be to the right. Okay, V cross B. Here's the magnetic field. Here's the magnetic field. Okay. Yeah. If I pass the current in the other direction, the force invert to the left. Okay, so it's keep on. If the frequency of inversion here is very high, you can tune this speaker to move very fast in this direction. Okay, at different frequencies to produce different sounds. That's the whole idea of the speaker. The speaker uses the magnetic force to produce sound, to produce sound waves. Okay, and applications, right? Let's take a look at applications. Applications of the above equation. Loudspeaker. Huh? Speaker, right? Speaker. So one, see the illustration in the book. In the book, that is going to be 21.18. 21.18. One, what are the devices? A permanent magnet. Two, a current, so a generator. Okay. Let's see. A source, okay, of AC current. Okay, a source of AC current. That's what your receiver is all about. Okay, your receiver is a source of AC current. A source of AC current, a cone coupled to a cylinder, right? And a wire, a conducting wire, wound around the cone. Okay, that's how you do it. So those are the basic components of the speaker. Those are the basic components of a speaker. Components of a speaker. Permanent magnet, a source of AC current, a cone coupled to a cylinder. Conducting wire wound around the cone. Okay. The way it goes is like that. The conducting wire is placed next to the is subjected, right? Subjected to the magnetic field of the permanent magnet. Okay. When the current in the wire is 0, there is no magnetic force. However, when we turn the current in one direction, the magnetic force is applied, right? A magnetic force is applied to the wire. 3. When this current is inverted, the magnetic force is inverted as well. So now we have this cone that's going to move back and forth, depending on the frequency of the source of the source of AC current. Okay, depending on the frequency of the AC source, right? The cone of the speaker is going to move back and forth. Is going to move back and forth. Okay. At that specific frequency. That's what produces the sound waves. Different sound frequencies can be produced by varying the frequency of the current. Okay, so that's how we produce sound of different frequencies with this device, just using the magnetic force applied to a current carrying wire. Okay, and then I want you to do an example here as well. Okay, here you go. Check your understanding. If the current carrying wire is parallel, if the current of the wire is parallel to the magnetic field, then the force must be 0, right? Here the force is going to be maximum. Here the force is going to be maximum as well, because the motion of the charge is perpendicular. Here is also perpendicular. Here's the magnetic field is vertical, but the wire is into the paper. The current is into the paper. And then we have an angle here. There is still be a magnetic force, but the magnetic force is going to be less than here or here. Okay? The magnitude of magnetic force here is going to be the same as here. Okay. So let me save the other one right in here. What else can we do? Let's see if I have an illustration for. Oh, here's another example of a current carrying wire. Let's see here. There's no magnetic field there, unfortunately. Okay, so I'm not going to do this one. The book, let me see if the book has this one. This is another device that we create using magnetic fields. Okay, let's see if your book has that. I don't see it has. Yeah, that should be torque in a current carrying wire. Yeah, it doesn't have that one. Okay, so let's move forward here. I must have an illustration of the. Okay, here you go. Okay, so here you go. We have here the case of a loop, a current loop that, by the way, is going to be subjected to a torque. Okay. So here you go. Here's another. Here's this loop. The plane of this loop is making an angle. If you look on the side, you're going to see the magnet. Here you go. You rotate this illustration, you know, to the. Okay, you rotate this illustration to the left. The magnetic field is going to point to the right. Okay, here you go. Here's my loop. Now I'm looking at my loop from the side. I need you to study that carefully at home. Okay, it's sometimes difficult to visualize something like that because it requires a 3D type of graph. And then what we have? We have loop number one. Loop number one now, arm number one. The current is going into the board. Arm number two is behind this other arm, which is arm number four, is flowing this way. Arm number three is coming towards you, and arm number four, we close the loop. Can you picture that? So it's something like that. Here you go. It's going to be a piece of paper would be better to illustrate that. It's going to be like that. Okay. I'm going to stop sharing so you can see better. Okay, so here's my current loop. Here's my current loop. I4 is flowing this direction. I1, I2, I3. Okay. I1, I2, I3. But this loop is a little bit has a little bit of an angle here. Okay. When I turn it around, you know, I discovered that it has this orientation. Okay, here is going to be arm number one, arm number 2, 3, and 4. So that's going to be, this is supposed to be I1 here. It's a drawing mistake. I1 into the board, I2 here at if you are, you know, if in your, let me see here, in the case of you, right? Okay, in the case of your referential, in my referential is like that. In my referential is like that. But in the case of your referential, I1 is this way, I2 is this way, 3 and 4. You have to visualize that. Okay, and we have a magnetic field in the horizontal direction. Okay, that's how you manage to visualize this current carrying wire in the three-dimensional space, like that. In the case of your referential, right? I1, I2, I3, I4, and the magnetic field in the horizontal direction. I1 is in this direction for you, right? So I1 cross B, there will be a force applied to that. Now I can go back to my PowerPoint slide. Here you go. Okay. There you go. Now we're going to do the right-hand rule here. Okay. So here you go. I1 cross B. Here you go. Palm of the hand. I'm going to put my B field right here. Okay. Here you go. Palm of the hand cross B, right? Palm of the hand in the I1 direction cross B. The force is downwards. So we produce this downward force that you see right here. Okay. What about the other ones? Current going into the board. What about I2 here? The arm number 2. I2, you cross with B, you produce a force into the board that I didn't illustrate it here. Let's see, must be illustrated here. Yeah, here you go. F2 is illustrated here. See that? F3 is going to be in the opposite direction of F1, right? Here you go. I'm going to put my magnetic field there as well. magnetic field right in here. I3 cross B is gonna be upwards. And that's exactly what you see here. F1 downwards, F3 upwards. Right? But then you're going to have F2 into the board, F4 going towards you. Now, the interesting of those two forces, those two pairs of forces, that is going to just stretch your loop. We are assuming that those loops are very solid. It cannot be stretched, okay? So the net force in this direction is going to be 0, okay? The net force in this direction is going to be 0. And there will be no torque either. It's not applying any torque whatsoever to this in this direction. But what about here? Here, you're going to have the following. Here, you're going to have a component that's going to be parallel to the circuit, and another component that's also going to be parallel to the two arms. This component of the force doesn't produce any torque whatsoever. But this perpendicular component does. Okay, this perpendicular component is going to make the loop rotate in the clockwise direction. And this component of the force is also going to make the loop rotate in this clockwise direction. Okay, producing a torque. And let's see if I have a drawing here of the torque. Okay, I'm going to do this one right here. Torque, in this case, torque is equal to 0, right? There you go. I'm going to write that down here. Net force is equal to 0. Equal to 0. And produces no torque. Like that. Because the only effect those F2 and F4 force that is to try to stretch your loop of current. But because the loop of current is rigid, you know, it's not going to go anywhere. This situation is different right in here, right? The situation here is different. In this case, you're going to have a component that's going to be parallel. I'm even going to want to make things easier here for me. Let's see. Right angle triangle. Here you go. That's my right angle triangle here. And I'm going to rotate a little bit. Okay. Here you go. Just a little bit. Okay. Here you go. Right angle triangle. And that's the component. Oh, I hate this triangle. This triangle is terrible. Huh. Okay, we have to do it in a different way. I'm gonna do it by the. Here you go. One component is going to be along the arms of the loop, right? This component doesn't produce any torque whatsoever. It just tries to stretch the wire. Okay, here you go. Same thing here, right? F1. I'm gonna put it in black color to be consistent. And those forces I'm gonna put right here in the middle of the current carrying wire. I1 is into the board. Here's the component of the force. And then we're going to have another component of the force that's going to be perpendicular to this wire. Okay. This force produces a torque. Okay, torque. This component produces a torque in the clockwise direction. I'm going to draw here for you. Right? And then I'm going to put color here, red color. Torque in the, just like that. And then we have this other component as well that I'm gonna stretch a little bit. This one has to be a little bit shorter. This other one a little bit longer to become more realistic. Right? Similarly here, we have something similar here. And then I have to invert the direction of this arrow. Okay, like that. And this one also produces a torque. The net force here is going to be 0 because this force here is the same as this one, ILB sine of theta, right? There is an angle between the current. The angle between the current is 90 degrees. Okay, so it's ILB here, ILB here, ILB upwards, ILB downwards. Net force is 0. However, net force is 0. What's going on here? Here you go. Net force is 0. However, the torque is greater than 0. Okay. Both forces produces a torque in the same direction, even though the forces, the net force is 0, the net torque is not 0. Okay. So we can go, we have here the angle theta, right? And here's the direction of rotation of the loop. The direction of rotation of the loop, because the torques are summing in the same direction at this position. Okay. So let's document that in the now. Torque in a current carrying loop. Okay. 1. Loop makes let's see, take a look here. Okay, 4 arms of the loop. Loop has 4 arms. Loop has 4 arms. Arm 1, 2, 3, and 4. Okay, 4 arms. Arms 1 and 3, right? That's arm 1 and 3. Arm 1 and 3 is perpendicular to the magnetic field. Are perpendicular to the B field. Arms 2 and 4. What about arms 2 and 4? Arms 2 and 4 makes an angle, let's say an angle theta with the field. Arms 2 and 4 makes an angle theta with the field. Arms 2 and 4 make an angle theta with the B field. Okay. Force in magnetic force in arm 1, magnetic force in arms 1 and 3. Magnetic forces are I let's see, I put what's the lengths? Arm 1 and 3. A, okay. Arm 1 is A, arm 2 is B. Yeah, arm 1 is A, arm 2 is B. Yeah. Arms 1 and 3. Look at 4 arms, okay? We gotta put a little bit more here. Arms 1 and 3 have lengths A. Arms 2 and 4, that's important. The length is important because the force depends on the length, right? Arms 2 and 4 have length B. Arms 1 and 3 are perpendicular to the B field. Okay. Force applied to arms 1 and 3 is, magnetic force. I'm going to put here magnetic force applied to arms 1 and 3 is IBA, right? Here you go. IBA or IAB. IAB. Arms 2 and 4 make an angle theta with the B field, right? I'm gonna put it here. You go like that. Look, arms 1 and 3 have elements that are perpendicular to the B field. Okay, arms 2 and 4 make an angle theta with the B field. Arms 3 and 5. Let's see. Arms 2 and 4. Magnetic force with arms 2 and 4 is sine of theta. Let's put it this way, IAB sine of theta. What else? Oh, here you go. We gotta be B here, right? Not A. It's B. Arms 2 and 4. What else? Magnetic force applied to arms 1 and 3 are opposite in direction. What does it mean? Net force equal to 0. Okay. But what else? There's one more thing. Magnetic forces applied to arm 1 and 3. Here you go. Arm 1 and 3. Hey, wait a minute. There is a mistake here. 1 and 3. Let's see. A. Arm 1 and 3. Okay. 1 and 3 is B, right? Let's see. Yeah, length B. Magnetic force. Oh man, I'm mixing up here. Arms 1 and 3 have a length. Okay, have a length B. Mixing up everything here. Okay, arms 1 and 3 have length A. Let's fix that. Arms 1 and 3 have length A. Okay. Arms length A. Yeah, 1 and 3, length A. Good. Arms 2 and 4 have length B. Okay. Arms 1 and 3, right, are perpendicular to the magnetic field. Arms 1 and 3 are perpendicular to the B field. That's good. Okay. Magnetic force applied to arms 1 and 3 is IAB. Okay, so that was, it looks like that was the only mistake I made here. IAB. magnetic force applied to arms on are opposite in direction, right? Let's take a look here. Are opposite in direction. Consequently, net force is equal to 0. But what else? Magnetic forces applied to arm on 1 and 3, not only they are opposite in direction, but are also collinear. Okay? Consequently, net torque is equal to 0. Okay, they're anti-parallel. Instead of collinear, let's put they're also anti-parallel. Okay, consequently, net torque is equal to 0. Okay, there is no torque applied to arms 1 and 3. Now let's take a look at arms 2 and 4. No. Oh, wait a minute. 1 and 3. Yeah. No. Anti-parallel. No. Mixing up. Sorry, folks. Arms 2 and 3. Yeah, 2 and 3 are perpendicular. Magnetic force applied to arms 1. Yeah, IA are opposite in direction. Net force is equal to 0. Okay, so here you go. Magnetic force applied are also okay. Magnetic force. Okay, magnetic forces 1 and 3 also makes an angle with arms 2 and 4. Consequently, net torque different of 0. Okay. Torque of arm 1 and 3 are what? With respect to this point, is going to be F3. Let's go here. That's going to be theta angle. You got to look at the angle here, proper angle. We're running out of time here. It's almost 11:30, right? Okay, so here you go. I'm going to, torque arm on 1 and 3, are in the same direction and reinforces each other. Okay. Now, what about 2 and 4? 2 and 4. Yeah, 2 and 4. Magnetic force applied arms 2 and 4 is IBB sine of theta. Magnetic forces applied to arms 2 and 4 are opposite in direction. Net force is equal to 0. Furthermore, magnetic force torque due to magnetic forces applied to arms 2 and 4. Net torque, are opposite direction. Net torque with magnetic force is 0. Okay. So let's stop here because we are running out of time. It's 11:30 already, and then next time I will review that again with you. It's a very interesting phenomenon, this one here. Okay, and you can only solve this problem by looking at those drawings. Okay, and drawing that, and also making your model of your three-dimensional model in front of you, so you can keep track of every force that acts in the loop. Okay, and 11:30. Let's see here. Any questions about that? So 5 minutes for the quiz. Okay, it opens at 11:35. Let's see how it's doing. How is the quiz doing there? Quiz. Let's see. Quizzes. Available 11:35 in 4 minutes. You have 15 minutes to do that. Okay, 11:50. So make sure you start at 11:35 so you have the full 15 minutes to do the quiz. Can you see the quiz there? Student view, right? I don't see the quiz. Interesting. Leave the student view. Let's see. Can I have upload the notes? Oh yeah, I'm gonna upload the notes. There's still time to do that. Yeah, thank you. Thank you for reminding me here. And save. Sometimes it takes, a while to save this guy here as a PDF file. PDF. As the file grows bigger and bigger, it starts to take longer and longer to save it. 3 more minutes before the quiz. Okay, now I will upload that for you. With the notes right here. No, that's not this one. Is this one here? 11:32, 27 of March. And I'm going to do that right now. Home. Notes. Okay. Files. P07. What is it? Notes. Okay, I'm going to erase this one and put my new one there. Go. Should be there. Now let's go to assignment home, right? Notes, and I have to file. Here you go. Add item. Now let's make sure we get everything for today. 1 more minute, and the quiz is going to be available. 3 questions, as always. Yeah. Okay, 11:35. Good. Loop has 4 arms, blah, 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 right? I'm going to cover it again next time. Don't underestimate this problem, okay? It's a little bit difficult. And so you need to get all the details. You need to do all those drawings. You have to sit down and look at it. So the notes are in there. 11:35. And home. Student view. Okay, so the quiz should be there now. Should be able to see it. Well, I don't see it. Why is that? Do you see the quiz there, by the way? It's number 4. Strange. Leave student view. Let's try it.
Quiz
Here.
number 4 is showing.
It's showing?
Yeah.
Strange. Why I don't see it? Student view. Yeah, I don't see it for some reason. Strange. Okay, so if you can see it, we're in good shape. Before 3 questions. Let's see, who doesn't see the quiz, please let me know.
Did you upload the notes, Professor?
Yes, it's in there.
Thank you.
Home. Notes, right here. And if you go to student view, notes right here. Okay. Okay. Let me stop sharing the screen. Please turn on your webcams. Once you're done with the quiz, you may leave, okay?